Hello everyone, welcome to this video. This video is provided by the Maritime Craftsman Society, and I am craftsman number 12. In the next two videos, I plan to share my experiences using WADAM for leveling analysis. This video is divided into two parts. The first part will mainly cover the relevant theory of leveling analysis, and in the second part, I will guide you through some hands-on practice. This video series only shares my personal experiences using CSOM during my studies and research. This video helps offshore engineering graduate students master relevant software to advance marine research. It contains no unauthorized or commercial materials, serving only for non-commercial academic exchange. This content is unaffiliated with DNV and is not official training. Alright, let's take a look at the fluid theory involved in leveling analysis. Regarding fluid theory, we have two basic assumptions. First, we assume that at the scale we are concerned with, the fluid in the flow field is incompressible and satisfies the continuity equation. Mathematically, this means that the divergence of the velocity, v, in the flow field is zero. This is the first basic assumption. The second basic assumption is that the flow can be described by a scalar potential, meaning that the velocity of the water flow is the gradient of the potential. Alright, next we combine the two basic assumptions. We substitute VE from the second basic assumption into the first equation. This gives us the following equation. The differential operator dotted with the gradient of the velocity yields our fundamental governing equation. In other words, at any point in the flow field, the Laplacian of the velocity potential is equal to zero. Then, based on the fact that velocity is the gradient of the potential, we can calculate the curl of the velocity, which is done by taking the differential operator cross the velocity v. If we substitute the velocity potential's gradient for v here, we get another equation. As those of you who have studied advanced mathematics should know, the differential operator crossed with its own gradient is always zero. This is independent of the form of the potential function, so the curl is zero. In other words, as we say, if there is a potential, there is no vorticity. Therefore, potential flow is also called irrotational flow. With the basic control equations established, let's take a look at the composition of the velocity potential. Because potential flow theory is linear, the velocity potential can be regarded as a linear superposition of three different types of potentials. The first type is the incident potential, which refers to the wave potential far from the structure. The second type is the diffraction potential, which arises due to the presence of the structure. The third term is the disturbance caused by the displacement of the structure, which we call the radiation potential. Since the velocity potential also exhibits harmonic motion, the latter part becomes an exponential term with e to the power of iot. A is the wave amplitude. Next, we need to consider the boundary conditions. At the water surface, this relationship can be derived from the Bernoulli equation, where x3 represents the vertical direction numerically. At the seabed, the velocity at the bottom is zero, which is when x3 equals negative h. Next are the boundary conditions generated by the radiation condition. Finally, there are the boundary conditions generated by the diffraction condition. For fixed structures, the directions of the incident wave and the diffracted wave are opposite, so there is an extra negative sign here. The above are the basic governing equations and boundary conditions of potential flow theory. However, in practice, due to the mixing of boundary conditions and the complexity of the geometric model, it is very difficult to obtain an analytical solution. Therefore, numerical methods must be used. WADAM adopts the three-dimensional panel boundary element method, with the free surface Green's function as the core. The solution is obtained for the velocity. If you're interested, you can learn more about the Green's function and the numerical implementation process. I won't go into detail about it here. After solving for the velocity potential, it needs to be converted into the pressure on the surface of the object. Then, it is further transformed into discrete, generalized forces, and finally, the 6 degrees of freedom motion is solved. Let's take a look at the Bernoulli equation. If we want to solve for the pressure P, it consists of two terms. The first is the static pressure. Then, there is also the dynamic pressure in front. If we take the partial derivative of the velocity with respect to phi, as can be seen from the previous equation, what remains is I omega. This term. Then, the pressure P determined by the Bernoulli equation can be substituted into the generalized discrete force formula. and we can use the small omega alpha to replace the mode function and the previous modal displacement phi alpha. If the velocity is expressed as a superposition of linear velocity forms, as in Formula 3, then Formula 2 can be written as shown here. We see that the term related to omega squared is called the added mass. The term related to I omega is called the added damping. The term related to displacement is called stiffness. If we move all these terms to the left side of the equation, we will find that the added mass term is included in the mass term. That's why we call it added mass. This also explains why we call them added damping and added stiffness. The final equation we obtain is the equation of motion for heave control. Well, the entire process from the susceptibility just discussed to the equation of motion for translational movement forms the theoretical foundation implemented in the WADAM calculation. In the next video, I will walk you through how to perform frequency analysis step by step. If any of you still have questions about the above theories, feel free to leave a comment below the video, and I will answer them for you.